When we hear the word infinite, we tend to simply think of it as being just an unimaginably large number. But that's not what the word actually means at all. The word infinite has two parts, the prefix in and the word finite. The prefix in means not, and the word finite means having limits or bounds. We use the word finite in mathematics just as we use the word infinite. To be finite means to have boundaries, while being infinite simply means lacking at least one boundary. We run into the concepts of the finite and infinite many times. In geometry, for example, a line is an infinitely long, straight object, while a line segment is a finite portion of a line. So here we've got a line. The arrowhead indicates that the line continues forever in this direction, as well as in this direction. So there's an arrowhead on either side, which means it continues forever in both directions. Because the line is never stopped, it is unbounded in this direction. It therefore has infinite length. And I want to be clear, if it had an arrowhead on one end, but none on the other, so it actually stopped on one end, it would actually still be infinite. It would just be infinite in one direction. So we would say it's still unbounded in that direction, but bounded on the other. Here, I have marked 2 points and the region that's between those 2 points on the line. This portion of the line between these 2 points is called a line segment, literally a segment or part of the line. These points are the boundaries of the segment, which makes the segment a finite length. Another common misconception about infinity is that it is a number or a value, but it's not. It's a description, a quality of a value. This means, for example, that you cannot add something to infinity. Even if it were a number that you could do this to, you would just get infinity as the result. So infinity plus anything is infinity. Nor can you multiply infinity by almost anything, because you would again just get infinity. Infinity times anything is infinity. There are actually circumstances where you can perform an operation on infinity and get a result other than infinity. For example, as long as you're only working inside of the set of integers or natural numbers, 0 times infinity is 0. Multiplying infinity by infinity also just gets you infinity. Raising infinity to any exponent greater than 0 will get you infinity as well. So infinity times infinity is infinity, and infinity to the power of anything is also infinity as long as x is greater than 0. Most of this is pretty understandable without any explanation at all when you think of infinity as an always growing quantity that escapes your ability to give it a single value. But what about the other operations, like subtraction or division, or raising it to the power of 0, or raising it to a negative power? Well, in order to understand what can go a little funny with infinity when you try to do certain arithmetic to it, we have to more thoroughly understand what infinity is and how we use it in math. As stated, infinity is not a number, it's a description. It tells you that the value that would go there is actually not bounded and therefore is unendingly increasing. But not every infinity is the same. For example, 2 to the power of x as x approaches infinity. In other words, the exponent is continuing to grow forever, which means the value of 2 to that power is going to keep going forever. So in this example, x is approaching infinity forever since it's unbounded, but the expression 2 to the power of x is also increasing, and it's doing so a lot faster than x is too. So when the expression reaches out to infinity, it's actually a greater infinity than x will be at any time along that trend. Which leaves us with a question. If we see infinities in an expression, how would we possibly know which infinities we were looking at? Which ones are greater? Which ones are lesser? Are they even possibly equal? Could two infinities made the same way even be equal? I talk a lot on this channel about values. For example, the expression 3 plus 5 has a value, and we know that value is 8. Let's say that the 3 and 5 come from us counting marbles from two separate bags. When we put those marbles together, we can count how many there are afterwards, and there would be 8. This is what addition is for, after all. But the two concepts we've just covered are actually different. One tells us that the expression 3 plus 5 has the same value as 8. The other is just keeping a count of marbles. This seems like a strange distinction, but hear me out. The expression is a calculation. The other is a count of discrete, meaning individual, natural, that is, physical and countable, objects. The expression has a value. The bags have cardinality. Cardinality is just the number of individual objects counted. Cardinalities are measured only in natural numbers, that is to say, non-negative integers. If you rip a card in half, you're holding the pieces that make one card. But you're still holding two things. The two pieces together have the value of one card. They combine to make one card. But they are two discrete objects. How many integers are between the 2 points on this number line? So we want to know how many integers there are between 5 and 11. Well, we can count them very easily. That's 1, 2, 3, 4, 5. Okay, that was easy. We're going to add one rule about counting these numbers, though. Since we're trying to keep track of what numbers we count, it is best if they are in numerical order, whether it's from least to greatest or greatest to least. This creates what's called a well-ordered set of numbers, set just meaning just any group. We can be sure we got them all because we can see that there's no gaps when we list them. 6, 7, 8, 9, and 10, those are the ones that we counted, the first, second, third, fourth, and fifth numbers in the set. We call this a finite set because it has a beginning and an end. It has boundaries, thus it is bounded. It is also countable because we can place the numbers in order without suddenly sticking something in the middle of our count. That'll make sense in a moment. Okay, so how many integers are there? Well, here is the integer number line. We can see there's 0 in the middle, and then it continues forever in both directions. In order to keep track of these numbers, we're going to expand our set in both directions, switching between the positive and negative values starting from 0. Here's what I mean. So we count 0, then we count 1 and -1, and then we count 2 and -2, then 3 and -3, 4 and -4, and so on. So here, 0 is the first one. 1 and -1 make 2 and 3. 2 and -2 make 4 and 5. 3 and -3, they make 6 and 7. So then the 4s are going to be 8 and 9. The 5s are going to be 10 and 11. The 6s are going to be 12 and 13. The 7s are going to be 14 and 15, but the -7 is off the line. This still produces a well-ordered set, because although we are putting a number at either end of this set each time we count, we aren't suddenly sticking a number between two other numbers. So I didn't put down a 0 and then a 1 and then all of a sudden realize that I had to put down 0.5 or something like that. Even though this set is infinite, because it does not have boundaries, it is unbounded, we still say it is countable, because we don't have numbers appearing in the middle of the ones we just counted. Thus, it's called a countable infinity. It is countably infinite. How many numbers are between the 2 points on this number line? I want you to notice that I changed a word from the last time I asked this question. I am no longer asking how many integers there are. I am asking how many numbers there are. The answer is not 5. It is so much more than 5. So how many numbers are between the 2 points on this number line? How do we figure that out? Well, between 5 and, let's say, 6.3, we've got 5.1, 5.2, 5.3, 5.4, so on and so forth. We just sort of blew up or zoomed in on a little section of the number line here. Now we're going to do that again. We're going to zoom in on a little section of this number line right here. And we can see that there's a lot of numbers between there. We can keep doing that. Every time I start back over, I can just stick another 0 into the number and have all new numbers that start earlier than the ones I had before. So if I have 5 and I try to go to 6, well, before I do that, I could just do 5.1. If I try to go from 5.1 to 5.2, well, before that, I could just go to 5.11. Or even if I'm trying to go from 5 to 5.1, I could go instead to 5.01. And instead of going from 5 to 5.01, I could instead go to 5.001. And every time I do this, I am getting a number that is closer to the thing that I am being asked to count from. So because of this, just between the numbers 5 and 6, there are infinite numbers, which means between 5 and 11, there must also be infinite numbers. So let's say we were asking someone with an eternal lifespan who could, in theory, count forever to count how many numbers there are. This creature, or whatever it is, some kind of, eternal number goblin, would have a big problem on its hands. Numbly, I've named it now, you cannot stop me, would know to count the number 5, but then it would have a problem on its hands. It looks at you pleadingly and asks, what is the number after 5? See, Numbly here is going to have the same problem we just had. When trying to find the next number, it'll try something like 5.1, but then it can stick a 0 in there and get 5.01. And then it can do that again and get 5.001. And none of these numbers are the next number, because it can keep doing this forever. And because of this, we can say that this is an uncountable infinity. And an uncountable infinity is much, much greater than a countable infinity. There are as many integers as there are numbers between any two numbers you pick. The distance between any two numbers is called an interval. And there are an infinite number of intervals on the number line. So that's an infinite number of infinities. That's so many more numbers. But the other big takeaway from this, actually the more important one for what we're about to do next, is that there is no such thing as a quote-unquote next number. For any number you actually choose to be the number after any given number, I can always reduce it by an extremely small amount and create a number that's closer to the original. For example, if you say that the number after 5 is 5.01, I'll just stick a 0 in and say that no, the next number is 5.001. Then you can do the same to me and say no, the next number is 5.00001. And then I can say, oh yeah, well I'm going to subtract 0.000003 from that and get 5.000097, which is closer to 5 than any of those previous numbers. Okay. What does any of that have to do with the topic of this video, which is actually repeating decimals? Here we go. We're going to start converting some fractions to decimals. A fraction is just a division problem, right? So, what we're going to do is 13 divided by 2. All right, I know that I can take 6 groups of 2 out of 13. And 6 groups of 2 is 12, and when I take that 12 out of the 13, I'm left with 1. In order to get the smaller values, the decimals, I'm going to have to start adding in that infinite set of zeros that's after the 13. Because after any terminating number, like 13, there is actually an infinite number of decimal places. But since they're not worth anything, they're all just zeros. So here I stick on that 0. I bring it down to this remainder here. This remainder, there's now effectively 10. I can take 2 out of 10 5 times. 5 times 2 is 10, and 10 minus 10 is 0. This is called a terminating decimal. To terminate means to stop. The decimal portion, 0.5, is read as 5/10, which means it's actually representing a fraction. 5/10 is the same as 1/2. Here you can see I've just stuck in a vertical line at the decimal point. And what this shows us is that and you might notice here that this remainder just before we started dividing into the decimals was 1. And the numerator on that 1/2 is also 1. And that's because the 0.5 is actually the conversion of 1/2 into a decimal. All right, let's take a look at 53/8. We're going to do 53 divided by 8. I can take 8 out of 53 6 times. That's 48, and when I take that 48 away, I'm left with 5. Okay, stick on a 0, bring it down. Now, how many times can I take 8 out of 50? I can take it 6 times. Again, 6 times 8 is 48. 50 minus 48 is 2. Put on another 0, bring it down. That's now 20. I can take it twice. 8 times 2 is 16. 20 minus 16 is 4. Put on another 0, bring it down. We now have a 40. How many times can I take 8 out of 40? Well, that'd be 5 times. 8 times 5 is 40. 40 minus 40 is 0. Now that we're at a 0, we're done dividing. So 6.625. This is also a terminating decimal. The decimal portion, 0.625, is read as 625 thousandths, which means, again, it's actually representing a fraction. 625 thousandths is 5/8. Take a look at here. When I stick in that vertical line and I look at the last remainder that I had before I went into the decimals, that was a 5, which is also the numerator of the fraction. 5 divided by 8 is 0.625. What about 28 thirds? Okay, so that's going to be 28 divided by 3. I can take 3 out of 28 9 times. 9 times 3 is 27, and 28 minus 27 is 1. Stick on the 0 and bring it down. How many times can I take 3 out of 10? Well, that would be 3 times. 3 times 3 is 9, and 10 minus 9 is 1. Hold on. In the previous step, I got a remainder of 1. And now I got a remainder of 1 again. This must mean that I'm just going to keep getting 3's in the quotient forever. 9.33333333, and so on and so forth. This is a non-terminating decimal. It does not stop. Because the digits in the decimal expansion loop, we call this a repeating decimal. The 3 dots at the end is called an ellipsis and means that we are continuing on. It sort of means and so on. We could make that decimal expansion much shorter by saying 9.333 and so on. That would be enough to show the repeating part of the decimal. But there's another way to show it, which we read as barred, which looks like this. We put a little line over the 3 because the 3 is the part that's repeating, and we read this as 9.3 repeating, or the way that I prefer to say it is 9.bar3. So here is a list of the more common repeating decimals that you get from converting from fractions to decimals. We're going to try to find some patterns. Here we have 1/3 is bar 3. 2/3 is bar 6. That shouldn't be too surprising because 2/3 is twice of 1/3. So twice of 3 would be 6. 1/6 is 0.1 bar 6. And 5/6 is 0.8 bar 3, which means there's actually a part of the decimal expansion for these two fractions that is not part of the repeating part. So 1/6 is actually 0.1666666, and 5/6 is 0.8333333. We will see this with repeating decimals formed from even denominators pretty frequently, but not always. The gaps in the sixths are actually already taken care of by values we already know, because 2/6 is 1/3, which we already have listed. 3/6 is 1/2, and 1/2 is just 0.5. And 4/6 is the same as 2/3, which we have listed. The ninths are really interesting, and we're going to cover them a lot. 1/9 is 0. bar 1. 2/9 is 0. bar 2. So you could imagine, for example, 7/9 would be 0. bar 7. For the ninths, the numerator is the number under the bar. And as I said, we'll be coming back to ninths a lot. They're very important for this. 11ths. 11ths are pretty interesting. 1/11 is 0. bar 09. 2/11 is 0. bar 18. So we've got a 9 and an 18, and then you could imagine 3/11 would be 0. bar what? 27, because they're all just multiples of 9. That's interesting. So for the 11ths, we multiply the numerator by 9, and the result, when written as a 2-digit number, becomes the number under the bar. So what if I had 10/11? 10 times 9 is 90, so it would be 0. bar 90. In other words, 0.909090. And that's different from 1/11 being 0.09, because that's 0.090909, which is actually a lot smaller. The sevenths are pretty interesting. The pattern in the sevenths is really interesting, and I want you to see if you can spot it when I show you the next ones. So here's 2/7. And yes, you can just double the previous value, but what else do you see about this? Because when I do the trick for the sevenths, I don't just double the previous value. Notice that the same 6 numerals are used every time. Notice that they're also always in the same order, if you think of them as a loop, which they are because they are repeating forever. So if we go back to 1/7, which was bar 142857, we can think of that as a loop. It goes 142857, 142857, 142857, 142857 forever, right? Well, if we take a look at the 2/7, right? 285714. I'm going to sort of emphasize when we hit the 1 so that you can hear where it loops. So 2857, 142857, 142857, 142857. Do you notice it's just that loop again? And the 2857, that's part of the loop. 142857, it's in there. Okay, moving on. Here's 4/7 and 5/7. How do you know which digit to start with? Well, since there's only the same 6 digits, we can list them in order so that the decimal expansions increase as the fractions increase. So those 6 digits written in ascending order are 1, 2, 4, 5, 7, and 8. Now we just choose the digit in the position corresponding to the numerator. If the numerator is 5, we go to the 5th number. So 1, 2, 4, 5, 7. It's 7. And then we fill in the numbers by copying the next 5 digits after 7 from the loop. So if we start at 7, we get 7, 1, 4, 2, 8, 5. And there it is. Think you can get 6/7? I'm going to wait just a second to see if you can figure it out. Okay, here we go. There it is. We go to the 6th number, which is 8. We find 8 in the loop, and we go 8, 5, 7, 1, 4, 2. All done. How about the 99ths? Remember I was talking about how ninths are going to show up a lot. Well, ninths are going to show up a lot, and so are 99ths, and 999ths, and 9,999ths. All of the things that are just a set of 9s in the denominator. Here we go. So 34 divided by 99. Well, I can't take 99 out of 34, so I put a 0 there. I'm going to add another 0 into there. 99 is basically 100, so how many times could I take 100 out of 34? That would be 3. And 99 times 3, that would be the same as 100 times 3 minus however much I had added on to the 100, which is 1 times 3. So 100 times 3 is 300, minus 1 times 3 is 3. 300 minus 3 is 297. And then when I subtract that, I get 43. And that's the kind of arithmetic I'm going to use to get through this division a little quicker. I'm going to stick another 0 on there and bring it down. So I'm now dealing with a remainder of 430. How many times can I take 99 out of 430? Well, 100 I could take out 4 times. So I put a 4 there. 99 times 4 is the same as 400 minus 4, which is 396. And when I subtract that, I get 34. Hold on. Hey, look at that. The 34 shows up again. So we see the 34 repeating in the remainders, which means the 2 digits of our quotient will therefore continue to repeat. Because I'm just going to take away another 297 in the next step, which is going to give me 43, and then I'm going to take away 396 in the step after that, which is going to leave me 34 again. So it's just going to alternate between me taking away 297 and 396, each of which correspond to the 3 and the 4 in the quotient. So 34/99 is 0.34, which is just the digits in the numerator. I wonder if the same thing's going to happen with 704/999. So here we've got 704 divided by 999. I can't take 999 out of 704, so I put a 0 there. I give myself another 0. Okay, 999 is basically 1,000. I can take 1,000 out of 7,000 7 times. 7 times 999 is 6,993. When I take that away, I'm left with 470. Okay. All right, well, 47, but it becomes 470 when I stick the next 0 on. So, my bad. I can't take 999 out of 470, so I stick a 0 on there. Don't even bother subtracting because I didn't subtract anything. Let's just go to the next 0. Stick that on there. How many times can I take 999 out of 4,700? Well, again, 999 is basically 1,000, so I can take 1,000 out of 4,700 4 times. And then 999 times 4 is going to be 3,996. Yeah, cool. I did it ahead of time. I'm just trying to do it in my head. Sorry. And when I subtract that, I get 704. Oh, look, 704. Boom. We see the 704 repeat in the remainders, which means the 3 digits of our quotient will therefore continue to repeat. So 704/999 is 0.704. The 34. 34 itself is the same as 3 times 10 plus 4 times 1. This is the concept of writing a number in expanded form. Basically, you're recreating all of the place values of the digits. Because the 3 is in the tens place, you would multiply the 3 by 10 to get the 30 that 3 actually indicates in the number. 704 would be the same as 7 times 100 plus 0 times 10, because there's no tens, and 4 times 1. So now here's 29 999ths, and I am claiming that it is .029. Well, notice that 999 is a 3-digit number. So what I'm going to do is I'm going to figure out the 3 place values for the number 29. It only shows 2, so I'm going to stick in the third, which is the hundreds, and there are no hundreds, so that's going to be 0 times 100, plus 2 times 10, plus 9 times 1. Because the denominator in this case has 3 digits, we can expand the length of our numerator to match by filling in the empty space at the front of the number with zeros. Therefore, 29 simply becomes 029. All right, one more example. 8 over 99,999. Well, 99,999 is a 5-digit number, so I need to stick on enough zeros to make 8 a 5-digit number. Well, that would be 4 zeros. So it's going to be .00008. Here we see 1/9 is 0.1 repeating, which is 0.11111. Here's 1 over 99, which is 0.01 repeating, 0.010101. Here is 1 over 999, which is 0.001 repeating, so 0.001001, so on and so forth. And we keep going. 1 over 9,999 is 0.0001 repeating, so 0.00010001000100001. Okay, so I get 4 nines, and then there's 4 digits under the bar, and that's how it works. However many nines there are is how many digits there will be under the bar.